Okay, we're going to talk about the homework. Again, real world example. And so there was a little bit of discussion on how many buses are in the system, and I just said, go ahead and look at your per unit diagrams and then figure out where your buses are based on your per units. So you can pick whatever one you want, but here's, sort of a general one that I would do. I would say this is bus 1, right? Because you can see you have a transformer here. This is bus 2. So on both sides of the transformer, I have a bus. I don't bother putting one in the cable, although if you were in the real world and you were using a program like Aspen, this cable right here actually has an impedance associated with it. And because there is an impedance associated with it, you actually have to have the element in there, right? So the transformer and the cable would look like that. Power systems analysis tools don't know how to add impedances in series, believe it or not. So what they do is they just put a bus in there and then just do a regular old Y bus. This is called a tap or a node bus. And essentially a tap or a node bus, the way it's processed in the applications that you're using, it does exactly the same processing for a regular bus. It just doesn't display the results for the user, the power user essentially. Okay? And in Aspen, you can convert a tap bus to a normal bus just by clicking a box. It's a pretty simple process to do that. So let's continue on. 1, 2. You'll notice here's another bus because it's another transformer. And I had 4 buses because even though it does actually not show the actual bus connection, I simply show that as being 4 separate locations. And why is that important? Well, because if you're analyzing the system, you have a bunch of 34.5 kV loads, some 6900 volt loads for the generators, but you also have some 480 volt loads, right? And you are responsible for designing a protection system that provides protection for every bus. You can't have an unprotected system no matter how small it is. Even 120 volts has to be protected. How's it protected? MCCBs, right? What are those words? What do those letters stand for? Molded case circuit breakers. Okay? So molded case circuit breakers are fairly important in terms of protecting some of the smaller loads. What's a smaller load? Well, obviously your house, 15 amps, 20 amps, maybe 30 amps for a 2-pole breaker if it's a dryer, 50 amps if you're getting to a range. They're talking about getting up to even bigger breakers because anybody heard of some of the new charging systems for cars? Tesla just introduced what's called a level 3 charger. That's supposed to be able to recharge the standard Model 3 from 0 to 75% in something like 15 minutes. So really high power levels. And the only way you can do that, right, the supercharging stations they have all around the state and all over the country, those are running at 200 kilowatts DC. Really high powers. You're not going to have 200 kilowatts available at your house, but if you have a 200 amp supply and you can run a 100 amp 2-pole breaker to your car to charge it, you can charge things mighty quick. So probably not going to be at your house, but what if you're going to Dysarts and you want to, you're traveling from point A to point B and you got a long way to go, you stop and get quote unquote gas, which means you plug it in, you run inside, go to the bathroom, grab a drink, stretch your legs for a minute, and then you come back out and your car is 3/4 of the way charged. And they say that the new Tesla, there's a new one, coupe, that's supposed to have a 600-mile range. So it's just a matter of time, right? I mean, it's already 300 miles is not that unheard of, and that's a car you can buy for 35 grand. So in 10 years, 600 miles will be nothing. And how many people here have their car can get more than 600 miles on a full tank? Under perfect conditions, I can probably get around 450 to 500 on mine. Perfect conditions mean I take the seats out. I don't eat breakfast that morning. Strip out all the carpeting, all that stuff. Drive it in granny mode. I mean, that's going to be where it is. So anyway, let's get back on track. So here's our buses. We have 4 buses. So your Y bus is going to be a 4-bus system. So all you need to do for drawing your diagrams for positive or negative sequence, and let's move this up a little bit. I'm going to have my reference bus. Okay. I've got my 3 generators, which I'm going to have my 3 power supplies with their internal impedances, right? And then that, as you can see, connects to one single bus. This right here, whoops, is bus number 1. Then I go from bus number 1, I go through my transformer, and now I'm going to connect to another transformer, but in between there, I'm actually going to force bus number 2. So I'll draw a strong line and force number 2 to go that way. Okay? So I've got this transformer right here. I'm on to that transformer's already, that transformer's already taken. Great. Wish that it would stick with it, but it doesn't want to stick with it. So here we go. So here's my transformer. Now I'm on bus number 2. I'm going to go, and in one direction I go out to who knows where, right? But that's essentially at bus 2, so I'm not going to worry about it because I have no information on the system over here. So I'm just not even going to bother including it because I have no idea what the impedance is, no idea what's going on there. So I don't care. So I'm going to swing off of that bus, and then I'm going to go through another transformer. And at the bottom of that transformer is bus 3. Then I go through another generator, which gets me back to my reference bus. And I'm almost done, except I have, off of bus 2, right, I have another transformer going to some load. So I'm going to actually draw that impedance, and this is bus 4. Okay?
And if you just did 3 buses, you could just not have the 4 on there and just have that.
You could neglect that, yep.
It's coming off of bus 2.
It's coming off bus 2. If you see here,
So you're not doing the one off of bus 1?
oh no, wait a minute, that is bus 1. That's the wrong location, so you're correct. This one should be moved to bus 1, not bus 4. So it goes here to bus 4. Okay? Questions on the positive or negative sequence? The only difference between positive and negative sequence, at least for our purposes, is these sources. In negative sequence land, those are removed. So all these admittances are X1s. So X1 of that generator, X1 of the next generator. Transformers, they tend to have always the same impedance, so these are always the X1s, right? The actual values that you'll use here, it depends on where you are in the time frame. So you can look at symmetrical currents, you can look at asymmetrical currents, which include some DC offset, and that's based on time. So there's some exponential decay. So you can actually see some asymmetrical fault values that happen that are much higher magnitudes in the first few cycles than they are at steady state. That's because all these inductors in here, they store energy, and they can dump energy out to go ahead and increase the fault currents. So when you're looking at fault currents at a very short time frame, like half a cycle after the fault has occurred, you're looking at peak currents. That's what the system has to withstand. That's called the withstand rating. But then maybe 2 or 3 cycles later, you actually have what's called an interrupt rating. So what the breaker has to be able to withstand is different than what it interrupts, and it's different because of that DC decay, that exponential decay. So when you buy breakers, and we've talked about that in this class, do you remember how I said KAIC? Have you remember that term? You can look back at the videos, but I'm pretty sure I said KAIC is, this is 1 times 10 to the 3 amps of interrupting current. So when you specify breakers, you go to Home Depot and you buy those molded case circuit breakers for your house. Most of those are rated for 10,000 KAIC. But they actually can handle a little more current because some DC offset. The general rule of thumb is the withstand rating is about 1.6 times the KAIC. And a lot of times when you do breaker coordination, so if you, and I don't know if anybody here has done that, but you can actually look at what fault current levels are and you can actually see, can the breaker actually handle it? So there was a question here from somebody about, actually I think it was Dan, who talked about why they put these reactors, these inductors, in series with these circuits or systems, and why not resistors? Well, resistors do consume real energy, so those are consuming watts. That's energy into the system. If you put inductors in there, they don't consume any real energy, but they can reduce the fault current levels. And all distribution circuits, they don't make distribution equipment that has greater than a 10,000 amps interrupting rating. So if you have more than 10,000 amps of available fault current at your distribution center, you're putting some reactors in series with those, because you got to knock the fault current down to what those can break. So all those fuse disconnects, you can see with a hot stick, we have a fuse that has to pop in. The fuse may or may not be able, to handle the 10,000 amps. Usually fuses are fine. It's all the system itself. It has to swing up. It has to have current going through it. And if you have more than 10,000 amps, you literally could damage the fuse cutouts, reclosers. All those could be damaged. But does 10,000 amps seem like a lot of current?
Yeah.
Actually, it's nickels and dimes. I worked on a system in Washington, D.C. that had 210,000 amps of fault current. So when you have current levels that are over 200,000, you use something called current limiting fuses, and some of the distribution circuits actually use current limiting fuses, because what they do, what happens when you get sand really hot? Turns to glass. And so what happens is they actually have a bimetallic element that goes through some sand. As this bimetallic element heats up, it converts that sand into glass, and then it actually changes the inductance, the resistance, to super high values. So it knocks the fault current down because you've got glass. And if you can actually see a fuse, that actually you can see some of the glass that has been converted. It's pretty crazy. So if you can Google, cutting open a melted fuse, current limiting melted fuse, you might be able to find some you can see where the glass is. Pretty interesting stuff.
So it's 1 times 10 to the third of...
That's K, right? It's just a K, or kilo?
Yeah. Of the fault current?
Nope. KAIC is this breaker, or whatever it is, can interrupt 10,000 amps of current without being damaged. That's what the 10 KAIC stands for. Okay? Do we need to actually build Y-bus, or do you feel like you can build Y-bus pretty easily? You can build Y-bus, right?
No, I guess for the 0 one, we should build one.
Well, I'll do it for 0, but for positive and negative sequence, you can probably do that pretty comfortably. So what did I do when I built my positive and sequence diagrams? Did I even give a hoot about how the transformers were connected? Did I once tell you to look at how the transformer or the generators were connected? Don't even care. This has 0 to do. Why is that again? Help me out.
Because it's balanced current.
Keep talking. Because it's balanced currents. What does that mean?
So there's no current flowing in it.
Grounding it isn't going to change.
If you have a balanced current, if it's going into a Y, and the balanced current sums at the neutral, how much current has to go into the ground? 0, because it's balanced. So whether there's a neutral there or not, the balance system doesn't care, because it sums to 0. So it couldn't care less if there's a ground or not, because it's 0. It sums to 0. So it's irrelevant. You can have it connected or not, and the a positive or negative sequence diagrams doesn't even care. That's a pretty important thing to help you understand sequence diagrams. You should highlight that in your notes. Why do I not care? Because it's perfectly balanced. They will always sum to 0. So whether there's a connection or not, the neutral connection sees no positive or negative sequence current. So if you think about that, that'll help you understand where you're looking for your sequence diagrams and connections. What does matter a lot more is our 0 sequence, because those do sum to a non-zero value, and they do need to have some flow. All right? So you see here, I have a connection to neutral. And here, and here, and here. So I'll just call those the same value, some neutral impedance. Let's just say they're all equal to Zn. They don't have to be, but we'll just all make them equal to Zn. So the generators themselves don't care about 0 sequence. It's really how are they connected to neutral. If they are connected, great. If not, well, then you got a problem. Over here, This is Z0 of the generator. It's just going to pass right through because internally in the generator, this is all you have, right? The generator is 3 separate windings that go in and out. They aren't connected until you see this connection right here, which means they're combined together. And then that is actually taken to neutral. All right? So the generator itself looks just like a transmission line, doesn't it? It's actually what happens to the connection downstream is where it makes a change. So rest of the system is fine. Now I got to go through some transformers. Do you care which transformer? Do you want to go to bus 4 or bus 2?
2.
All right, so we're going to go to bus 2. So we see this transformer is delta Y grounded. Delta Y grounded. So my transformer, delta Y grounded. Here's my 3-phase diagram. So in the delta, I'm not going to focus on the delta. I'm going to focus on the Y because it's usually easy to start. If I have 0 sequence current flowing in here, at least from the Y's perspective, is the 0 sequence current allowed to flow into the neutral? Sure, there's a connection here, right? So from the Y's perspective, yes, I can do that. What matters, though, is whatever mantra time, whatever flows in the primary has to flow in the secondary, right? You haven't been working on your mantras over the weekend, so that's okay. What's that? Forgot what mantra meant? So what flows in the primary has to flow in the secondary. Can a current in here flow through here? Well, as long as that current can flow through here and flow through here, right? So these are all 0 sequence current who all have the same value. So that current circulates in the delta. This has to equal 0, doesn't it? All those currents have to be equal to 0. But I can have 0 sequence current flowing in the delta side. I just can't have current enter or exit the delta side of the transformer. So from this perspective, there is a connection here. So this is bus 1. This is bus 2. Here is my reference bus. You can see that on the Y side, which is going to be connected to bus 2, I can have 0 sequence current entering or exiting. On bus 1 side, I can't have any current. So this is an open connection. This comes up, and this is the 0 sequence current for the transformer. So that's how that diagram is shown for that one.
Where are your generators?
I haven't drawn them yet. I'm just showing it individual transformers. If you want, we can actually start to do that now, if that would be helpful. I do not know how to make these two link together. It's really frustrating. It's almost like I need to lock it. Let's try locking it. Huh. I do not know how to lock these, so all right, let's see if I locked it now. No, said I locked it. Okay, let's try that. Nope, that didn't work. I don't know. I have no idea. Sorry, I don't know this application well enough. I have to spend more time on it because this does not seem to be working. So let's try to see if I can zoom out. No. Well, it's not going to work. So let's just, I'll erase all this. You'll have to go back. I apologize, but see if I can make this bigger.
You locked it. It's never going to erase.
You're right. Some of it erases and some of it doesn't. It's whatever is locked. I thought I unlocked it all.
It's okay, Bob. We can.
Help. I just don't know why it won't allow the background to be moved with it. It doesn't make any sense. So anyway, now I can move it. So let me just erase it. I guess I'm going to have to. So let's hit that and trash it. There we go. Oh, it's erasing the actual lines. Weird, okay. Temporarily. All right, so now we're going to go ahead and we're going to look at the actual representation. So I'm going to move this up just a wee bit, give myself as much room. So I have my reference bus here. And then I have my generators coming up through my reference bus. So I've got my impedance, 3ZN, 3ZN, 3ZN. My generators now. And now I'm at bus 1. Okay? So we'll just call these Z0s. And you got that. Now we're going to go to bus 2. And we said that we're connected from bus 1. And I'm going to, because I don't have a ton of room, I'm going to put this connection here, which is going to not connect to bus 2, right? It's going to hang in the air. And this connection is bus 2, which does have a connection through the transformer to reference, right? So you can see here, there's no connection between bus 1 and bus 2 because of the delta. That breaks it up. Now I look at my next transformer, which is going to be this one, which is delta delta. So at bus 2, I want to come off, but I cannot connect to bus 3 because the delta prevents me from connecting to bus 3. And there is no connect. Why did that happen? There is no connection between bus 3 and reference because the delta just circulates inside the delta, right? Yes, question.
Are those 3 ends where you have XO and XO, would those be 3 Z's as well?
Here?
So I'm just not sure why the 4th generator wouldn't also have a 3 Z.
I'm not at the 4th generator yet. I haven't made it there. I'm right at this transformer, so I'm heading on to the generator now. Okay? So this is bus 3. There's no connection to bus 2 or bus 3 at all, right? So those are terminated. And now I'm going to go into my generator, which has a Z0 and a 3ZN associated with it. Okay? Now I'm going to go and do my final one, which is bus 4 over here. You can see that is another delta Y transformer. The delta is connected on bus 1. So that, we'll put that down over here, is open. And then bus 1, or bus 4, is here. And we just show the impedance of the transformer connected there. Okay? Questions on that? Any questions?
I missed the 3ZN part. I forgot about that. So what do you just take I had Z, that's just your impedance of your generators.
Well, isn't there an impedance associated with neutral? Is that 0? There's a transformer in there with an impedance, right? How can you make that 0? Isn't that going to limit the ground fault current?
Yeah.
Remember we talked about a high resistance grounded system, low resistance grounded system, and zero impedance grounded system, or solidly grounded system? Are those solidly grounded?
Yeah.
They are?
Or no.
They look like they're grounded through transformers, so these are high impedance grounds, and that is important to include that in there because that's going to limit the ground fault current, isn't it? If I had zero sequence current flowing through here, that's going to be a lot lower if this is included than if it's not included. So now, my Y bus for my zero sequence, and if it's helpful, 2, 3, 4, 1, 2, 3, 4. These are the self-admittances. So here's the other very important thing. These elements here, right, this one and this one, are in series with each other. Those have to be added together, Z0 plus 3Zn, and then that has to be inverted one at a time to give me the generator zero sequence impedance. Right? They have to be added together first before you invert them. So this is going to be 3YG0, right? Because I've got 3 generators connected there. And that's it. Is there anything that goes between bus 1 and 2? No. Anything between bus 2 and 4? Nope. So these are all zeros. Because I've got 3 of them. It's only 3 times that because it's this element here plus this one plus this one. Those 3 added together. Question?
Yeah, so I'm still confused with the Z naught and the 3. So I only had one Z value.
There's 2 of them, right? You've got the transformer.
How do I get to?
You have the generator has an impedance, doesn't it? X0. And you've put an impedance externally into the neutral, right? So you have 2 impedances that exist there. This is not a solidly grounded system. It's an impedance grounding system. The transformer essentially, so here's your neutral that goes, this is actually to ground. This actually literally runs through a transformer with, I think in this case, it has a resistor through it. So that resistor actually looks like a really large resistor that goes to the generator phases. So this is the actual high impedance ground. You've got a big resistor represented in there because of the reflectant of the turns ratio, right? This is a 7200 to 240 volt transformer, which means whatever this resistor is, Rn, it's going to be Rn times A squared on this side of the transformer, right? On the primary side of the transformer.
So where do we get the, is that in the data sheet for the generators that we find?
Just put, for this case, you just put 3Zn. If I wanted you to actually calculate fault currents,
Well, that's okay. I'm asking.
I would.
So when we build the Y bus, it's 3 times the 3 impedance because there's 3 generators. So
It's 3 generators, but the 3Zn is there because why? No. How many zero sequence currents do you have flowing through neutral? 3, right? So you can see in the generator, I actually have these 3 Z0s here.
So for this one, we would ignore that 3Zn almost because we don't.
No, why would you ignore it?
Just add it, and you just want the representation in the Y bus.
I have to,
that's there.
I don't want it. It has to be included to accurately calculate what the ground fault current is. It's not, I want it. It has to be there.
But I mean, we don't know that number.
Yeah,
So
so how
like
do we get that number?
J20.
Just say 3Zn.
Okay. I'm just saying, all the other values, we have actual,
Yep.
23.
Would you want me to have given you the value, or would you could just have put it in there as a matrices or equations? I could give you the value.
My question was.
Did anybody want to resubmit the homework with the actual value on Thursday?
It's not really changed. You just add in the value.
You just add in the value, yeah. It doesn't change anything. You can't ignore it, though. It's very important not to ignore it. All right? Does that make sense? Ralph.
Could you go over again really quick why the delta for the negative sequence both go to reference? Because I know.
Negative sequence? Negative sequence, it doesn't go to reference.
Oh no, this is the zero sequence that we're looking at.
Right. Positive and negative sequence, they don't go to ground. They just can pass right on through.
Yeah, okay. Then the only thing that changes with the negative sequence is that you just
You take out the generators.
for the positive sequence.
Correct. I didn't finish my discussion on this, right? Why do we have 3 of those? Because this here, each one of these 0 sequence current is flowing in each leg of the generator. Those all sum to be there, right? So if I wanted to actually calculate the actual voltage drop across that actual Zn, how would you include it? How do you calculate the voltage drop? This one over here only has a single current going through a single resistor, right? Or a single impedance. This one has 3 of those. So I can try to figure out as showing it as 3 times the current, or I could just multiply this by 3 and then just show a single current going through there. Okay, does that make sense? This is super, 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 super important. If you can do anything with the utility systems, understanding all this stuff, if you understand it, it's going to really set you up well, because it takes people years to understand why are things grounded the way they are. Why do we get 0 sequence current? Why do we not? And by far, the trickiest, nastiest thing I've ever done is ground fault coordination. It's always the hardest thing to do. Even though you say, we'll put a delta Y transformer in it, sometimes you can't do that. I just completed an evaluation that I started 5 years ago to check for coordination of systems with the Eversource utility system. So this is that big generating facility in Western Mass. They've been working hard to get their system coordinated, and I just did something last week that they actually aren't coordinated. So I sent that out, and 5 years of work, and it's still not coordinated. Guess which one is not coordinated? The ground. It's always the gotcha. Ground is the worst, most difficult one to coordinate. The one that I told you about that happened in 2015 or 2014 at Millstone that tripped off a 2 nuclear power plant facility and ended up causing an unusual event was a result of an uncoordinated ground system. So, for what it's worth. Okay, so are we ready to build Y bus? Continue. So we look at bus 2. All we have is this transformer. What is that? T85. So this is going to be Y85-0. And then that's it, right? There's nothing else that's connected, so that is going to be 0 and 0, 0 and 0. For bus 3, we have the generator connection, which is going to be, again, these two have to be summed together in series. So we'll just call that YG0. No connection. And then for bus 4, we only have the transformer. So that's transformer T86, or is it 85? I think it's T80, it's 83, 85, must be 86. So this is Y86-0. So remember you were saying there's a lot of zeros? Is that a good thing? Sure is, because remember how I said how difficult it is to coordinate ground systems? Look how much easier it is when you don't have an interaction of 0 sequence current flowing between bus 1 and 2. I can check for coordination of bus 2 completely independently of bus 1. There's no impact because 0 sequence current doesn't flow through it. It makes it much, much, much easier to do that. So this system is well designed from a perspective of ground current, except this one here, right? Because if this generator breaker is open, so let's pretend to draw the breaker here open, bye-bye your ground reference. So this whole system right here, however long that is, that's all not protected from a ground fault. So if a ground occurs, it doesn't change anything. You don't get increased fault currents. You don't even know what happens until you close the generator, and then probably bye-bye generator. But I made that comment, and they didn't do that.
Is that because so those currents would be in the delta, floating in the delta, when you make that connection?
No, there's no, where is the ground reference? So this is a really good drawing. I need to flow back to this point here. This whole bus is ground, right, is reference. If this breaker is open, right, essentially what ends up happening is this connection is gone, isn't it? So if I have a fault to ground here, how do I get electrons to flow through back up?
You
They don't flow through. They're prevented from flowing back up. So it's an ungrounded system. It's just like your house. You don't know it. Ethan, did you have a question?
I did, but the guy asked.
Okay.
Are those values supposed to be negative, that diagonal from the Y bus, or are they positive this time?
It's the other ones that are the opposite of.
You only subtract the negatives here. These are just, the diagonals are just added up. They tend to be negative because the transformers and generators look like resistors and inductors. So when you invert an inductor, it becomes a negative J term. So you only have negative J's because you've inverted it. Notice these are all Y values, right? They're not Z's.
Okay, so that's only true with Z's that you have that negative, if they're inductors.
If they're inductors, yep. Questions on the homework?
So you were just looking for the diagrams and Y bus to be constructed, but nothing to be solved?
Yeah, because you haven't gone to chapter 9, which is how to actually solve for fault currents. Haven't gotten there yet. But I could have said, what if you get a three-phase fault at this bus, how much current would you get? How would you do that?
You need to know the resistance of the voltage.
If it's a three-phase fault, there's no resistance, right? All three phases are connected together. So how would you calculate the fault current at a three-phase fault there?
Would you just take the power divided by the,
What power?
whatever power's, I don't know what bus you're at, but whatever power's supposed to be flowing
The
through
voltage.
that bus?
Actually, fault currents have nothing to do with power.
You need the voltage and something else.
Yeah, so if we run so the process to do that, right, is here's how you do fault currents. Step 1, well, actually, let's back up. So step 1 would essentially be model your system. Draw one line, right? Step 2 would be calculate your Y bus for your system, right? Which Y bus would you calculate for a three-phase system fault? Three-phase fault. Boy, I can't wait to start writing the next test.
Your ground, your reference point.
Three-phase fault. What type of a fault is that? It's a balanced fault, people. So calculate Y bus for positive sequence. You only have to do positive sequence, right? You don't have to do negative sequence or zero sequence because it is a balanced fault.
Because all three are faulted.
All three are faulted, yeah. They all see the same impedance. At step 4 is calculate V Thevenin and Z Thevenin at bus of interest, right? Whatever bus that happens to be. So in this case, we said it was bus 1. How do you calculate those two? Well, if it's an unloaded system, right? If there's no load, your V Thevenin is whatever your V of your generators are going to be, right? If there's no current flow through the system, it's whatever your generators are. How do you calculate Z Thevenin?
Did you say it was 0? No.
Better not be 0, because how much fault current would be flowing through a 0 impedance?
No.
It'd be infinite amount. So in the real world, you don't have infinite amount of current.
You have to add up all your per units. Yes, you have.
Add up all the per units. You want to do this for a homework? All right. Next homework. What is Z Thevenin for positive sequence? So that's your problem. That will be your thing. So for your next homework, I would like you to tell me what the three-phase fault current is at all 4 buses. in actual amps. So per unit is wonderful, but when you go buy a breaker, do you buy a breaker in per unit current or buy it in amps? Does this make sense? What to do?
No, I mean, no
Well, you
one
got 2
knows.
days to figure it out. You can also ask me for questions.
Yeah, so where would we begin?
Look at this video.
Yeah, I mean, right there, and then you got to calculate V-thevenin, which is your going to be your V of the generator.
Yeah, so let's just say it's 1 at an angle of 0.
So there's your V-thevenin.
So I'll give you a huge hint. Now what?
The per units are
I've already told you what to do next. Solve for Z Thevenin. Once you have Thevenin equivalent impedance, so this is bus 1, right? I can model my entire system as this, right? Isn't that what Thevenin told me? I can take an entire system and replace it by its Thevenin equivalent impedance and with a voltage source, right? When I put a fault, I'm essentially just closing a switch, aren't I? If it's a 0 impedance fault. So do you think you can solve for I when the switch closes?
yeah.
You sure? To me, it's V Thevenin over Z Thevenin. Last time I asked Mr. Ohms, or Sir Ohm, or whatever he was. Okay?
So was the statement about just adding impedances
That was wrong. The statement of adding impedances is incorrect. It's a good guess, but it's not.
You have to go down through, see what's in parallel, that's the series, the whole, analyze the circuit.
You can do that if you want. You can go do series parallel combinations all day, every day if you'd like. That's not what I would do. I would have a different way. Maybe if you look at chapter 2, you might find some clues. This is the painful part of learning, right? But you've already learned this stuff. Or did you? Did you hear it? Kind of learned it? Put it in the back of your brain? Forget it. Now you're going to learn it. Do you want me to make it a much bigger penalty if you don't learn it? This homework's worth 1,000 points. And you can't ask me for help? No partial credit. You either get it or you don't. Your almost entire homework grade would be based on this one problem. What's that? No test or final? You sure you want to do that?
If we get it right,
If you get it wrong, though, that means that you get a 0 for your homework average, which means you're already down to an 85 on your average. Who wants to take that bet? I don't know if I would do that. Breyer's like, maybe I would.
The software all is gonna do this for us.
What software? You have software that you can use?
In real life, when we do this.
Yeah, but you know how much software costs? 10 grand? Anybody here got 10 grand to buy some software?
school does.
School does? Some companies do, yes.
I think we all spent more than that to be in this class right now.
You spend more than $10,000 to be in this class?
Summed up the total
Oh, yeah, fair enough.
in here per credit hour, I think you.
I will not make it that hard because I want you to learn. So if you have questions, ask questions, come see me. But it's actually really a very simple problem. If you look at the chapter 2 stuff, you'll see it.
Over the impedance, which is your admittance.
You're on the right track.
I'll just ramble over it.
I don't know how to do it without brute force.
You do not have to do it without brute force. If you look at chapter 2, there is a way to do it that's not brute force at all. All right, any other questions on the homework? Good homework problem, bad homework problem?
If it's a good one, we should call it a day and just go work on it. So.
I don't think so. Remember, you paid over $10,000 for this, right? So